All right, we're very happy to have Zhenkang Zhang, famously known as Kevin, who's going to talk to us about reshaping effective field theory analyses.
All right, thanks very much for the invitation. It's my great pleasure to be here. Today I'm going to talk about some works that I have done in the past few years on topics about effective field theories. And most of the talk will be based on these two papers that I wrote myself. And there are also some follow-up works, in particular with my PhD advisor, James Wells in Michigan, and also a group of junior collaborators. So the lack of new physics discoveries at the LHC is motivating us to seriously think about the possibility that the scale of new physics is actually much higher than the standard model weak scale and much higher than what we can directly probe experimentally. And this is the picture we have, and in this case, I would like to argue that the right framework to use for analyzing experimental data and connecting to our theory expectations would be an effective field theory framework. So the idea is that if we want to study a specific UV theory containing a group of BSM fields, in addition to the standard model fields and their interactions, instead of using this UV theory Lagrangian to directly calculate observables, we would like to make it into a process consisting of several steps. So first of all, we want to match the UV theory onto an effective field theory by integrating out the heavy BSM fields. And we end up with a series of effective operators that encode the effects of these new fields. Essentially, this is a matching step that establishes a UV EFT dictionary. And this effective field theory that we just obtained is defined at the scale of the heavy particles. So we need to run it down to the scale where we perform experiments via RG evolution. So this is a crucial step that makes the effective field theory framework appropriate, because in this step we resum the large logarithm, so our predictions can be more accurate. And finally, starting just with a series of effective operators at the experimental scale, we can compute observables such as cross-sections that we measure at the LHC and other experiments. So the highlight of this step is that it is a model-independent calculation in the sense that we don't have to specify a particular UV theory to do this calculation. We just start from a series of effective operators truncated at an appropriate order, and then the calculation can be done once and for all, and we know how the observables depend on these operator coefficients. And by looking at our experimental data, we can learn information about these operator coefficients. And later on, if we want to learn about specific UV theories, we would then go back to the matching step and see how these operator coefficients translate into the parameters of the underlying theory. So the EFT framework is actually well established, and it has been very useful for many decades, so what's new about it? So I would like to highlight two new aspects of EFT studies in recent years. The first new aspect is that we're having more and more data, especially from the LHC. And actually, for the first time, we can talk about a global EFT analysis. So not only do we have the ZPOL data and electroweak boson production data from back in the days of LEP in the 90s and 2000s, we also now we have LHC data, in particular Higgs data, and more on electroweak boson production data. So there are a lot of observables that have been measured experimentally, and there are many EFT operators that can contribute, that can affect these observables. So the whole analysis becomes really complicated. So the picture I would like to draw is the following. It would be, in the ideal case, we would want to use the full standard model of EFT, just write down any operator that is consistent with the symmetries of the standard model. But the calculation then will be really complicated, although you have a fully general calculation. So what we usually do to make the calculation more feasible is that we make assumptions to restrict ourselves to certain subspaces of the entire EFT parameter space. But we have to be careful because we don't want to go too far down the curve, because in the other extreme, there will be like very simple frameworks with just a few parameters that capture the new physics effects. These are indeed very simple, but they are not really general. They cannot be used for inferring the new physics in more general UV theories. So it's hard to find a balance, and in particular, I will talk about a simplified framework that people have used a lot in the past few decades, the triple gauge coupling framework. And in the first part of this talk, I will tell you why this framework is oversimplified and what the problem there is. So the second new aspect is that I think we're still learning new knowledge about quantum field theory. And there have been several interesting developments in recent years. For example, there has been proposed a scheme for counting the independent number of operators using Hilbert series has been proposed, and also it has been discovered that there is a holomorphic structure in the one-loop evolution of the standard model EFT, and also we have found using helicity amplitude techniques that there are certain helicity selection rules that means that for certain processes, the standard model and dimension 6 amplitudes do not interfere. So in that case, we really have to look for new channels and design new observables to get sensitivity to the dimension 6 operators. So just to add to this list, today I'm going to talk about some of my work, which is to do EFT matching calculations in a way that does not rely on Feynman diagrams. So here is the plan for this talk. There are two parts. In the first part, the topic will be new challenges at the LHC, and I'm going to talk about diboson production. And the key message here is that the LHC data is calling into question the interpretation in terms of triple gauge couplings. And in the second part, the topic will be new tools for one-loop matching, and I will talk about a way to match UV theory onto an EFT in a gauge covariant way without computing correlation functions that covariant diagrams. So just to be clear, we go back to the big picture. Part one of the talk will deal with this part of the graph, essentially how we calculate observables from series operators in a model-independent way, and in turn, what we can infer for the operator coefficient starting from our measurements and how to treat everything in a consistent way. And part two of the talk will deal with the matching part of the calculation, essentially how to establish a UV EFT dictionary. All right, let's get started on the first part of the talk and giving away the punchline, which is that it's time to go beyond the TGC interpretation for double pair production. So what's the problem here? It is often said that double pair production measures triple gauge couplings, or TGCs for short. So what this means is the following. When we measure double pair production at colliders, either from E plus or minus or from proton-proton, this is one of the diagrams that contributes, and it involves this triple gauge coupling vertex with a neutral gauge boson going to a pair of W's. So the form of this vertex is uniquely fixed in the standard model by gauge invariance, but if we have new physics, it can go into this vertex, and a general way, well, a standard way for parameterizing these new physics effects is to write down this TGC Lagrangian containing these highlighted parameters, which are called anomalous TGCs. So by definition, they are zero in the standard model, but they can be non-zero due to new physics. So the goal of this exercise is to use experimental measurements for double pair production to see what we can learn about these anomalous parameters, how far away they can deviate from zero. So this is a framework that people have been using since the 1980s. But the problem here is that if you think more carefully, what I just showed is not the only possible contribution from new physics to this process. And there is, first of all, there is another diagram, and second, there are many other parts of the diagrams represented by these gray circles that can be affected by new physics as well. So if we're just measuring the double pair production, how do we know that we're really looking at this TGC vertex? There is a common law that answers this question, which says that we have electroweak precision data, which actually constrains a lot of the new physics effects. And in fact, all of these gray circles turn out, it turned out that they can be constrained very well by electroweak precision data. So people usually say that since this is the case, then any new physics that could affect the power production must come through this TGC vertex. So this is rarely mentioned, but this is really what underlies the interpretation of the power production as a TGC environment. And this is what I will call the TGC dominance assumption.
So can you just remind us, if you making this assumption and if you fit these deltas, what are the current limits on these deltas? Are they at the level of 10%?
Oh,
the deviations.
Yeah.
The dimensionless quantities, so are they at the level of 10%, 0.1, or what are they?
I will show you the plot later, but the numbers are roughly for the LHC data, what they're claiming. If they only look at these TGC parameters, the numbers are about a few percent.
So they're comparable to the accuracy of precision electroweak. A few percent versus, I guess, part per mil or something.
Yeah. It's becoming comparable if you only look at those.
But it's not that, anyway, okay. But that's already telling you might be suspicious, right?
Yeah, well, I guess the data that I have is maybe a little bit outdated because this analysis was done some time ago. And with recent data, I think the constraints are becoming even stronger.
Okay.
Yeah.
What?
Actors, new result.
I have no idea.
This is Maria.
Yeah, I mean, already at 1.1, it's at a level of a few percent, and I guess since then, the level of constraint must have improved. That's what I remember.
Okay.
Okay. So the question is this assumption valid? And we want to answer this question by doing an EFT exercise. And this is the basic procedure for doing this exercise. So first of all, we write down the operators that can affect the observables that we're measuring. And then we work out their effects. And we're going to compare the effects of triple gauge couplings versus other BSM effects for the case of Lab 2 and for the case of the LHC. And we'll try to understand the results and see if there are general lessons that we can learn. So first, let's write down the operators. We'll work at the dimension 6 level, and here are the operators that can contribute to W pair production at tree level. And you can see that some of these involve the Higgs field, the gauge fields, and some involve the Fermion field as well. And as a technical note, I have adopted the ortho basis, but of course, physics is basis independent, and the conclusion will be the same in any other basis. So from these operators, we can calculate their effects on our observables, and they are conveniently written in terms of anomalous couplings. And they fall into three categories. The first category is what I mentioned before, the anomalous triple gauge couplings. And the second category is a W boson mass drift with respect to the Z boson mass. And finally, there are a bunch of parameters for vertex corrections, namely corrections to the Z and W to Fermion couplings. And each anomalous dimension in this slide, highlighted on this slide, is a function of the coefficients of the operators that you just saw on the previous slide.
So there are enough dimension 6 operators that you can independently vary all of these coefficients?
So an assumption that people usually make in any kind of global EFT analysis would be that we restrict to certain flavor structures. So if you consider all the flavor indices, no, we don't really have enough data for all of those.
Okay. But flavor conserving, you have all.
Yeah, that's right. Yeah.
Okay. Yeah. Okay.
So here are the expressions for these anomalous couplings in terms of the operator coefficients. And this exercise also gives us a counting of the independent number of parameters. So there are 3 anomalous TGC parameters, and there is 1 parameter for the W boson mass drift, and there are 7 parameters for vertex corrections in total, including 3 leptonic and 4 hadronic parameters.
So this is just my question is, sorry, just to be clear, so that 3 anomalous triple gauge boson couplings. I thought you had more than that in the general parameters.
The statement is that these are the 3 independent parameters at the dimension 6 level.
Okay,
Yeah.
but if I was doing a purely bottom-up analysis, there would be more parameters.
If you go beyond this power count, or
Yeah.
well, either you go beyond the dimension 6 level, or in some other power counting. Yeah,
Right.
that's possible. Yeah.
Okay.
Yeah. So it's the same reason for why I didn't write down the modification of W to fermion vertex, because they're not independent compared to Z vertex.
Okay. So there are sort of, yeah, there are fewer dimension 6 operators than you would have if you were modifying all these couplings just from the bottom.
Well, if you just like add arbitrary terms to Lagrangian, or make
Yeah.
arbitrary modifications to standard model terms in a non-gauge invariant way, yeah, that's the right
Yeah.
statement. But the exercise here is really to map out the independent ways of deforming the standard model Lagrangian. Yeah, so I would like to ask you to keep these numbers in mind. There are 3 anomalous TGCs, and there are 1 plus 3 plus 4 other parameters, and we'll compare their effects in a moment. So after this exercise, we can now formulate the TGC dominance assumption in a more precise way. So this assumption is really saying that in W pair production, the additional 1 plus 3 plus 4 parameters can be neglected because they are very well constrained by electroweak precision data. And therefore, W pair production can be interpreted as probing just the 3 anomalous TGCs. And of course, the question we want to ask is, how good is this assumption? And we're going to look at the following observables to answer this question. At lab 2, we take the differential cross-section for the semi-leptonic channel, namely one double decaying to 2 jets and the other decaying leptonically, because in this case, the full final state can be reconstructed, and so we can have a measurement of the differential distribution with respect to the outgoing, the angle of the outgoing W. And for the LHC, because this analysis was done a while ago, at that time I was using the ATV-1 data from the Atlas measurement, and the observable is leading lepton PT distribution from the fully leptonic channel, because this is the cleanest channel. So in the following, we're going to compare the anomalous TGC effects considered in conventional TGC fits versus the possible effects from the other 8 anomalous couplings that people really neglect in the conventional TGC fits. And in particular, we'll set each parameter to its 2 sigma upper bound and see how their effects compare. And these are taken from those references. So let's first look at the case of lab 2. So this is a plot for the fractional shift in d sigma d cosine theta as a function of cosine theta. 0 means no shift from the standard model. So if you turn on some of the anomalous couplings, you'll get something that's non-zero. So if we turn on the 3 anomalous TGC parameters up to the value that's claimed by the experimentalists that we're able to constrain, we get these solid curves, and we see that they are roughly consistent with the experimental errors. And on the other hand, as I mentioned, there are a few parameters that they actually neglected in their analysis, and we're going to see how much they can affect this observable. And in particular, there are 4 other parameters that can enter the calculation, and if we set their values to their upper bounds as determined by precision electroweak data, what we get are these dashed curves. And we see that in this case, indeed, these other parameters have a negligible effect on the conventional TGC analysis. So we're really justified by interpreting lab 2 data as measurements of triple gauge couplings. And this is a statement independent of the UV theory, as long as the low energy EFT can be described by a dimension 6 EFT.
It seems to me that all contributions can be comparable to one another in about close state of about 5 or so. Like they're in that region, they're somewhat close.
Well, you already take into account all the beams to do the fit. But each being is, well, these are not independent measurements, but can work out the statistics and do the correlation. But it's really taking, so you can think of the cross-section, well, or really the number of events in each bin as an observable. And you put everything, you put all the bins together, and also notice that this is only for a single center mass energy, and that put data at many different center mass energies, and you can put them all together.
Yeah, but also all the deviations at that point of cosine theta of around 0.5, all the deviations are small compared to the experimental error, so there's no real constraint.
So you just
from that region. The constraint is presumably coming from
these
near cosine theta equals -1.
Yeah. Actually, didn't.
Is there a reason why they all cross at cosine?
Yeah, I was thinking about that too. Yeah, it's,
They
something
all,
about
I
it.
mean, you can't, they don't exactly cross, but they all kind of cross. It's kind of weird.
Yeah, I don't have a good answer for that. Yeah, so
Does it have to do with sine squared theta w being small or something, or being close to a quarter, or one of those kind of things?
yeah, it could be. Yeah.
Okay.
It could be accidental. Yeah, I don't really have a good answer for that. I mean, it's really only just these parameters. I mean, for those, really, there's not a crossing here. Yeah. All right, now let's move on to the case of the LHC, and this is the leading up on PT distribution and the experimental data and error bars and standard model predictions, the dotted lines. These are all taken from the Atlas paper. And then if we look at the effects of these anomalous couplings, first if we look at the anomalous TGCs and we set them to the values that they claim to be able to constrain, we get these solid lines. So basically, these TGC fields are telling us that new physics effects cannot be larger than what is represented by these solid lines.
Where's the line for 0?
So this is the standard model prediction.
That's the standard. Okay, there it is.
These dash lines. Yeah, it's a little bit difficult to see over here.
Yeah.
But the thing is, there are other parameters, as I mentioned, that can affect the observables. And in particular, there are two of them whose effects are significant. And if we set them to the largest value compatible with electric precision data, what we get are the dash lines. So we see that they are far from negligible, and they in fact can be the dominant effect that you're constraining.
What are those operators again? Could you maybe just write them on the board?
Yeah, so just from the notation, I guess it's, you can see that it's the anomalous couplings between the Z boson and up and down type quarks for the right-handed quarks.
And is the point that somehow, are those somehow less constrained at LET because they focus, most of their precision comes from electronic observables?
Yeah, that'll be the content of the next slide, yes.
Sorry.
That's one of the reasons,
Okay.
yes.
All
Absolutely
right.
right.
Okay.
Yeah.
So we could interpret these as, well, okay, you're going to tell us, but.
Yeah, it's it's really a matter of interpretation. We have been saying that the double pair production measurement is interpreted as TGC measurements, but now we see, no, this is not the case anymore. And in fact, the TGC interpretation is no longer justified by electric precision data in a model-independent way. So of course, if you just have a BSM theory that only affects the TGC couplings, then it's still fine to use the TGC parameterization, but that seems like a really contrived set of BSM theories, because all these parameters, they can receive contributions from the same set of effective operators, so naively you would expect them to be correlated. So if you're saying you only have anomalous TGCs and nothing else, it will be really a fine-tuned or contrived new physics theory.
I mean, this suggests that, I mean, if you set out in your life to measure this coupling GRZU, you wouldn't do it by double gauge boson production, you do it by single gauge boson production, I assume. Because you're trying to verify that something is given by the standard model prediction to the highest possible accuracy, and there's just a lot more data there. So,
the amount of
is this
data,
telling us that you should be doing a bigger analysis?
Yeah, that's right. Yeah. So the amount of data is only one aspect of the analysis. There is also like at which energy you're collecting this data.
Sure.
So actually, I'm going to come to this on this slide. So
Okay, go ahead.
what is really making the difference between the case of Lab 2 and the LRC? And there are two main reasons for the difference. The first one, as Marcus has already mentioned, is really that the Z couplings to the quarks are less constrained than the Z couplings to leptons. And this is what we usually would just say that electric precision data constrains everything to percent or per mil level. But that's not really the case because the leptonic variables are better constrained than hadronic variables. And here it's really the uncertainty in hadronic variables that matters. There's a second reason which I think is more interesting and equally important, which is that the effects constrained by electric precision data are actually enhanced at high energy. So that's why I said it's not only the amount of data you have, it's also at which energy you're taking the data. So to see that, let's look at an example. This is for longitudinal double pair production from right-handed fermion pair. And if we look at the high energy behavior in this amplitude, we see that it contains a complete combination of 3 anomalous couplings. 2 of them are anomalous TGCs, and there is another one, which is the Z coupling to the right-handed fermions. So this parameter is indeed constrained by electric precision data, but its contribution to double pair production is actually not small because of the high energy enhancement. So in this case, we really cannot interpret this process as giving us information only on these 2 parameters, but it's really on the combination of all 3 parameters. And in fact, the reason why this is the case can be simply understood from the Goldstone equivalence theorem and dimensional analysis. And the relevant operators here are of the form h dagger d mu h times a fermion current. So there are 2 sets of effects that can come out of this operator. First, if you take the Higgs to its value, then pull out the Z mu out of the D mu, you see that it's a modification to the ZFF coupling. But this modification is only of order V squared over lambda squared. It doesn't grow with energy. So if you sit on Z pole, you can only get sensitivity to V squared over lambda squared effect. On the other hand, if we set the Higgs field to the Goldstone and pull out the partial derivative out of the d mu, we see that it's really a contribution to the fermion pair to Goldstone pair, which is equivalent to fermion pair to longitudinal W pair at leading order in the high energy expansion by the Goldstone equivalence theorem. And this effect actually grows with energy scales as E squared over lambda squared. So if you can go to higher energies than the weak scale, while still staying below the scale of new physics, so you can use the EFT, this process will really give you, can potentially give you a better sensitivity even though you have less data. And that's exactly what happens here.
But I mean, really, it's coming in at the same order as these triple gauge boson things, right? So in the high energy limit, these things are both entering linearly, right?
Yeah, that's right.
So I mean, to me, it seems like the first point seems like it's really the most important point because, I mean, a priori, the most naive thing, all of these effects that you're talking about are coming from dimension 6 operators.
Mm-hmm.
So you would, just very naively, you would expect them all to grow quadratically with energy.
Well, it depends
Very,
on
very
what
naively.
it depends on what observable you're looking at.
Yeah,
you have to be
yeah.
careful in the electric
Right.
broken phase.
But that is, for these observables, it does come in exactly that way, right?
Yeah, for W pair production, yes. But there are subtleties if you have symmetry breaking, because then there is another scale, which is the VEV, which is a
Right.
symmetry breaking scale. And if you have that scale, which is a constant instead of the energy in the numerator, then the story can change.
Right, but this is the fastest growth at high energy. So for high
Yeah.
energy observables, I think this is what I would expect.
Yeah, that's right. So in the high energy limit is really this linear combination to other linear combinations and other amplitudes that we can constrain the best.
Right.
So we can go one step further and look at what we can learn about the global EFT analysis program. So what people usually do is that we write down all the dimension 6 operators, under certain flavor and mixology assumption and so on, and work out the anomalous couplings that they can contribute to, which can be directly mapped onto observables. So there are 8 of them that are directly probed by electroweak precision data, and we already say that these 8 parameters are just so well constrained that we don't even have to think about them anymore in the rest of the analysis. And then we can just look at the anomalous TGCs for double pair production. But I just showed you that at the LHC, this is no longer the case, and in fact, we really have to look at this part of the table as well, because there are parameters in this part of the table that have enhanced effects at high energy. So even though they're well constrained, they cannot be neglected. And if we look further into the future, if we were to measure double pair production at a higher energy lepton collider, we have to look at this part of the table too, because the same story is happening. So really, we need to put all the parameters together into a global analysis. So I think what this is saying is that we're really setting new standards for global EFT analysis, which actually have already been adopted by various groups in the recent years. And also, a related direction that would be interesting to explore is that there can be new ideas that we can think of to take advantage of the high energy enhancement of certain scattering amplitudes. So instead of requiring more data, say at the z-pole, for observables that don't grow with energy, we can actually look for processes that have a better energy scaling and look at high energy data to get more precise information on the EFT coefficients. So this brings me to the end of part 1. So the focus was on this bottom-up part of the graph. So essentially we're trying to infer information on the effective operators from the observables that we measure. And I think this should be a dynamical process in the sense that as new data keep coming, we should be constantly rethinking about the conventional frameworks, and they should be critically examined to see if these conventional frameworks are still useful, whether we have to extend them. And the example that I just gave is that TGCs, they have been useful in the past, but they no longer serve the purpose of extracting general information of EFT operators from diboson data. And the key intuition here is that as we're going to higher energy, the conventional way of thinking about the EFT parameter space and the conventional interpretation of the experimental data are being challenged.
So I mean, one way you could look, I mean, that graph that you showed, that you're sensitive to these other couplings of W's and Z's to quarks, it says that those experiments are in fact sensitive to those. I mean, they're sensitive to those and the linear combination of other things as well. So I mean, it seems like it seems like, and you know, like I was saying, the reason that one is focusing on double gauge boson prediction is because people thought they were testing the triple gauge boson couplings. But if you were testing those couplings, you would just be looking. I don't see any reason. The first thing you would try would just be single gauge boson production, right? You look at distributions in productions of single gauge bosons, which has an enormous cross section and so on. So I'm just wondering, has that been done to some extent? I mean, have people looked at that?
Single gauge boson would be dominated by the z-pole data, right? Because there we're just sitting on the z-pole, and there is enormous amount of data. And that's what's setting the electron.
No, but I mean the couplings to quarks. I mean, the electroweak precision data. I mean, actually, I also don't quite understand why it should be so much worse. How much worse are the couplings constrained at LEP, the up and down quark couplings of the Z? I mean, it's not part per mil level, but it's what? What is the error on those, fractional error?
Yes, the percent level.
Percent or maybe even 3%.
Yeah. So it's a little bit worse than electronic couplings. Yeah, but still, there's information.
But I mean, it seems like, okay, but if you set out in your life to constrain those couplings in LHC, it seems like you could do pretty well then, right? Have people tried
If you
to
just
do
look
that?
at single gauge boson,
For example, I don't know, I mean, that might be the first thing you could try.
the thing is, at the LHC, there's a question of whether you want to look at on-shell or off-shell single gauge boson production. With these have different scales.
Right.
If we're looking at on-shell, I guess the sensitivity won't be as good as lead.
Right.
And for off-shell, if you go to high enough energy, the parameters you can probe best would be the 4 fermion operators. Simply because these operators, so the effects of these operators on the Z couplings, they don't grow with energy. So if you want to extract information on these operators using the high energy behavior, you have to look at something else, such as diboson production.
I mean, the scale there is roughly 2 times mz or something. It doesn't seem it's that high.
Well, it's quite a few times MZ. I mean, you go, well, this is around one data, you already go to
Okay, we'll just go to 9.
close to TeV, and going to is even higher.
Right. Okay.
Okay, any other questions before I move on to the next part? All right, now let's switch gears and look at EFT matching. And to remind you of the big picture, I'm going to talk about this part of the graph, namely how to derive an EFT from a UV theory. The conventional approach to EFT matching is that we use Feynman diagrams to compute a bunch of correlation functions among the light fields using the UV theory, and then we try to figure out what effective operators with what coefficients can reproduce these correlation functions. But this seems like a rather indirect approach, and in fact, I would like to introduce a much more direct approach to go directly from the UV theory to the effective operators without computing correlation functions. And as you probably have inferred from the name, it is a gauge covariant approach, meaning that the calculation is more elegant. So I have to give a lot of credit to the previous literature on this subject. So the early studies date back to the 80s, but these works have gone unnoticed for a long time until 2014, when Brian Henning, Zhenkang Zhang, Hitoshi, and Yama wrote a paper that reviewed this method and revived the approach. And later on, there were some follow-up works, and at some point, there were some criticisms because it was realized that there were some subtleties and problems in the previously developed framework that certain contributions certain contributions cannot be included, and those are the mixed heavy light loop contributions. In case you've heard about it, I will mention more later on. But of course, these problems turn out to be solvable, and this is where I started looking into this. In fact, we proposed a partial resolution to the problem around the same time as the Berkeley group. And of course, at that point, the problem really is that the calculation became more and more complicated, so the approach is kind of losing its original attraction of being more being simpler. So I think at this point what we really need is a way to organize the calculation, to put all the pieces together in a concise way, that can be systematic. And that's why I came up with this picture. So if we think about the way we use Feynman diagrams to do the calculation, of course there's this intermediate step, but there are also a bunch of intermediate steps from the path integral to Feynman diagrams that we learn in the first semester quantum field theory class involving the rate contraction for the perturbative series evaluation and so on. So these are technical steps that we do once and for all, and we never have to come back to them. And it's actually a similar story along this alternative route. And in fact, a lot of progress has been made in the previous literature on how to deal with these rather technical steps. And there are some subtle issues that people have found, and there have been proposals for how to resolve them. But at that point, I felt like we're really lacking a framework for putting them together to formulate it in a concise way. So that's why I came up with the idea of using diagrams, in exactly the same way as we use Feynman diagrams to incorporate this information. And in fact, once things are written in the diagrammatic language, we see that all the issues raised in the previous literature can be solved in a straightforward way. So I'm going to tell you briefly what the idea is, and I'll start with something very simple that everyone is familiar with. So the idea is that we want to work more closely with the path integral. We want to integrate all the heavy fields from the path integral for the EFT matching calculation. So at tree level, this is just given by the stationary point approximation. So we just solve the classical equations in motion for the heavy fields and plug the solutions back into the UV theory Lagrangian. And this gives us the tree level effective Lagrangian. At one-loop level, things are also quite simple because we use the background field method to write each field as a sum of the backgrounds, a classical background and a quantum fluctuation, and write out the first terms in terms of the quantum fluctuation fields. You see these are the terms that are quadratic in the quantum fluctuations. And at this order, the path integral is Gaussian, which means that it can be evaluated exactly. And the result is simply a functional determinant of this quadratic operator of the UV theory, QUV. So this is all familiar from the context of 1PI effective actions. And in fact, what I just showed is exactly what we would do if we were to compute the one light particle irreducible effective action, which is the Laurent transform of the path integral. And to be more precise, we take the logarithm of the determinant of the functional, take the logarithm of the functional determinant with a prefactor that depends on the spin of the particle. And just to show you a few more steps that are standard, log determinant becomes trace log, and the space-time part of the trace can be evaluated in a general way, and the result is an integral over space-time, an integral over loop momentum, and also a shift in the integrand on this so-called kinetic momentum operator that's related to the covariant derivative. So all this is familiar from the calculation of 1PI effective actions. But in the matching calculation, we're really interested in a different quantity. So what we want to calculate is the one-loop effective field theory Lagrangian and not the one LPI effective action. So these are different quantities. And actually, the relation between these two quantities has been the source of most of the confusion in the previous literature. But in the end, it turns out that we can show that there is a very simple relation between the two quantities, which says that the space-time integral of the one-loop effective field theory Lagrangian is given by the hard region contribution to the one LPI effective action. So what I mean by the hard region contribution is the following. We're using the method known as expansion by regions, which is actually standard in the field of higher loop calculations. So at one loop level, this method works in a rather simple way. Essentially, we can separate the loop momentum into a hard region and a soft region, where the loop momentum Q is on the order of the heavy particle masses and light particle masses, respectively. And the method is that we expand the integrand before doing the integration in each region. And the non-trivial statement is that if we just add up the contributions from the hard region and the soft region, we can reproduce the full integral. So to give you a little bit more intuition on how this works, let's just talk about a very simple toy model involving a light scalar field and a heavy scalar field denoted by lowercase y and capital phi respectively. So this would be one of the diagrams involving both the heavy field and light field in the loop that we would calculate in the UV theory for a 4-point amplitude. And the goal of EFT matching is, of course, that to figure out the local operators in the EFT that would reproduce this kind of amplitudes along the light field. So the hard and soft regions will correspond to the loop momentum beyond different scales. So if the loop momentum is on the order of the heavy particle mass, the entire loop would shrink to a point from a low energy point of view. So this is the corresponding piece in the EFT calculation. And in the soft region, the loop momentum is on the order of the light particle masses, while the heavy particles their masses are much higher, so the soft region really corresponds to just shrinking the heavy propagators to points. So this is the piece in the EFT that would give contribution to the photon amplitude. So this is what separates the hard itself, and the statement is that we want to extract the hard region contribution because, as you can see from this example, these correspond to the local operator, the one loop generated local operator insertions. And the soft region contribution, on the other hand, would correspond to tree-level generated operators inserted into one loop graphs. And the key intuition here really is that when we think about what 1PI effective actions are, these are quantities that encode quantum fluctuations at all scales, and that's why we can use them at tree level to encode all the quantum fluctuations. And also that's why we integrate over the entire momentum space if we want to compute the 1PI effective action. But the EFT action is asking for some different information. It's really what is the local piece in the low energy Lagrangian. And for that, we only need to extract the short distance information from the 1PI effective action. And that's why we take the hard region. So to go back to the equation, as we have seen, it's the integral of the log of the quadratic operator of the UV theory. And now the procedure is that we want to first expand the integrand in the hard region, and then do the integration for each term in the expansion. And in fact, this is the series expansion that will lead to the EFT expansion in terms of effective operators. So there are various different ways of doing this expansion, and we want to do it in a nice way, known as covariant derivative expansion, or CDE for short. So there is really nothing mysterious about the name, because a covariant derivative expansion is nothing but an expansion where derivatives are covariant. In other words, we never separate d mu into a partial derivative of the gauge field. The calculation can proceed in a general way if we just use the general form of the quadratic operator. As we can imagine, there has to be a kinetic term, a mass term, and these are different for bosons versus fermion. And there can also be a series of interaction terms. So this U would be the leading piece without a covariant derivative, and there can be other higher derivative interactions. We call that P mu is defined as ID mu. To give you a simple example, if we want to work out what a U matrix is, suppose we look at an example of a real singular scalar S coupling to the standard model of Higgs. This U matrix would contain different components. There is an SS component connecting an S field fluctuation and an S field fluctuation, and there is an SH component, there is an HH component, and so on. And if we just look at the SS component and see how this can be calculated, we'll have to look at how the S field interacts. And if this is a term in the UV theory Lagrangian, we can follow this background field expansion to work out that this component of the U matrix is really this coupling times the Higgs field squared. And also it's worth emphasizing that this quadratic operator is really a function of the covariant derivatives and the fields. So in the end of this calculation, we should still have some objects that is made of covariant derivatives and fields. And what are these? These can only be gauge invariant operators. And it is in this way that we have avoided the calculation of correlation functions and arrive at gauge invariant operators directly from the UV theory Lagrangian. So as I just described, the expansion, so the procedure for performing CDE is conceptually quite simple, but technically it can be quite tedious. So that's why I'd like to use a diagrammatic framework to keep track of this calculation. So the idea is that if we can collect identical terms in this expansion and encoding diagrams, and by enumerating the diagrams, we can recover the full expansion, just as the way we use Feynman diagrams. And in fact, the rules for doing so can be generally derived, and they turn out to be quite simple. And I won't have time to go over the derivation, but I'll just show you the results, and they're actually quite intuitive to understand. So each diagram would consist of propagators and vertex insertions. And the rules for propagators are a bit different for bosons versus fermions, simply because they have different kinetic amongst terms. There are different types of vertex insertions, including P insertions coming from the kinetic terms, and U insertions coming from the leading interaction terms. And analogously, there are also Z insertions, which I didn't list in this table, but they come from these higher order interaction terms, and their rules can be similarly worked out. And also, you will see some dotted lines in the diagrams. These are not propagators. These are used to mean Lorentz contractions, because as you see, some of these building blocks have Lorentz indices, and so we have to keep track of how their Lorentz indices are contracted with each other. So we want to use these building blocks and follow these rules to put together propagators and vertex insertions in all possible ways and contract the Lorentz indices in all possible ways. And that way, we can enumerate all the terms in the CDE. To give you a simple example, if we want to integrate out a complex scalar, this would be one of the diagrams that we have to compute. It involves 4 propagators, each one is 1, and there are 4 P insertions, each reads 2P mu, and their Lorentz indices are contracted, as shown by the dotted lines. So this is the operator structure contained in this diagram, and then we have to figure out what the prefactor is. And it turns out that there are also very simple rules for the prefactor. There is a spin factor simply coming from the overall factor of the functional determinant. And in this case, since we have a complex scalar, the spin factor is just 1. There can be a symmetry factor if the diagram has a Z-S symmetry under rotation. And in this case, S is equal to 4. So this avoids a double counting in the CDE expansion. And finally, there is a loop integral, which will be one of the master integrals. And which master integral to use depends on how many propagators there are and how many Lorentz contractions there are. And in the present case, we have 4 propagators and 2 Lorentz contractions. So Ni equals 4 and Nc equals 2. So the definition of these master integrals is the following. And in the present case, we want to just look for Ni equals 4, Nc equals 2, and here it is. This is the value of this master integral. So now, if we put all the pieces together, this is what we end up for what this diagram represents. So this is supposed to be one term in the CDE expansion. And what this is, it should be pretty clear, because if we're looking at what can there be for if you have 4 covariant derivatives, there can only be a G mu operator. And in fact, if you expand the commutators in the G mu, we see there are 2 pieces. And what we just got is exactly the second piece of the G mu operator. And as I just said, we have computed the coefficient for this piece. And in fact, this is the only possible contribution that can give us this operator structure. That means we can determine the coefficient of this piece in the EFT Lagrangian, and as a result, we can determine the coefficient of the whole thing. And physically, what this means, what this gives us is a threshold correction to the gauge coupling. So as a side comment, you might be wondering, what about the first term? And in fact, the first term comes from the other terms in the CDE that we haven't worked out. And it turns out that for technical reasons, there is an additional rule saying that there is only, we can obtain the full EFT Lagrangian by computing just a subset of the terms in the CDE. And this subset corresponds to covariant diagrams where a Lorentz contraction is between the adjacent p's only, such as this one. So in the final few minutes, I'm going to show you briefly a more realistic and more complicated application of the covariant diagrams technique. I'm going to talk about the matching from the MSSM to the standard model EFT, and I'm going to focus on just the renormalizable operators because they would give rise to threshold corrections. So what this means is the following. When we integrate out the BSM fields from the path integral, we not only get the higher dimensional operators, we also get additional contributions to the renormalizable operators that are already in the UV theory Lagrangian. So they serve to correct the renormalizable parameters across the heavy particle thresholds. So this is what we mean by the threshold corrections. And threshold corrections can be simply related to the coefficients of these renormalizable operators that we can compute from matching. And Susy threshold corrections are important for several physics questions, including consistent matching of the Higgs quartic, because the Higgs quartic is a free parameter in the EFT, but it has to be matched onto a combination of gauge couplings in the UV theory. And also, we can look at bottom tau unification, which would require a very specific amount of threshold corrections for the tau couplings at the Susy threshold. So we have studied these questions in detail in our paper, but for the purpose of this talk, I would like to highlight the matching calculation part of the paper. So it turns out that to get the full one-loop Susy threshold corrections in the MSSM, we only need to compute these diagrams. There are 30 of them, and each of them is easily computable following the rules that I just showed you. And in the end, we found full agreement with a much more involved Feynman diagram calculation in this classic paper. So I think this calculation serves as a rather non-trivial check of the technique, and also shows how simple things can be in this new method. All right, so this brings me to the end of the talk. To summarize, I have introduced what I call covariant diagrams as a systematic diagrammatic representation of functional matching of one loop. And the point is that we want to avoid the detour of calculating correlation functions, and as a bonus, we can preserve gauge covariance in all steps of the calculation, which makes EFT matching calculations easier and less error prone. And the key intuition I would like to emphasize here is that we want to work more closely with the path integral, and we want to extract information from the path integral. And for the matching calculation, we only need to extract certain amount of information to derive the EFT Lagrangian, and that part is the UV information. All right, I'll stop here. Thank you very much for your attention.
Any more questions?
Is there any hope for two loops?
Good. So if the question is if there is any hope, there is definitely hope, but it's just that we haven't looked at that in detail. Yeah, I think it should be, in principle, it should be extended. It should be extendable to higher loops, but it's just that the calculation is not done yet.
But the method of regions has been done in 2 loops.
Oh yeah, of course. Yeah, for higher loop calculations, I mean, it's been well known for a long time.
It's actually, there's no general proof of it. It's something that's kind of...
There's no gap?
I don't think there's any general proof of it.
Yeah, there is a paper that I quoted here, which is kind of recent, this one. And it seems this guy claimed that he was finally able to give a general proof. I don't know if I'm quoting correctly, so yeah, if it's not, then yeah.
Well, if there are no more questions, let's thank Zhenkang again.